p.m. at 1978. He put his MSc an excellent research group. His Excellency Dr. Hashim Yamani, the former Minister of Industry, and Professor Murad Ismail, Professor of Mathematics at the University of Florida. The publication exceed 100 refereed articles. Let me welcome Dr. Al-Haidari on behalf of KSU and ask him to deliver results.
السلام عليكم ورحمة الله. شكرا جزيلا دكتور، وشكر موصول لكم عدنيتوا عشان تجوا هنا. أعرف إنه الجامعة والمدارس مقفلة. أمس كنا بالطائرة وقلنا يمكن ما ننزل، أقنعنا من الظهران، ولكن الجو بدأ يعني يسوء للغاية، وكانت الهبوط صعب جدا حقيقة. we were lucky to make it. فلله الحمد أنا معكم اليوم. حياكم الله جميعا. أنا الحقيقة ذكرني أحد من الزملاء إني أول مرة جيت الجامعة هنا وألقيت فيها محاضرة كان 1986. I think most of you were not around at that time. يعني few of you old timers were here. It was in the physics department at that time. وآخر مرة أظن جيت ألقيت محاضرة أظن في 2010 أو المهم about 10 years ago. At that time كان في شيء يسموه في الفيزيكس جرافين، وأظن له علاقة شوية في الماث. we're talking about يعني too technical stuff. اليوم لا والله I will be talking about very general يعني topic. وما كنا ندري إن الجامعة يعني تصير الظروف وتقفل. كنت أتوقع كثير من الطلاب من الهندسة والعلوم يجوا، لكن looking at the corridors يبدو إنه أعضاء هيئة التدريس أكثر من الطلاب. ف يعني I apologize if the talk is a little bit dilute. لكن I'll try to make it interesting for you. At least it's challenging for you. I make claims, very bold claims, and I'll try to show you that we succeeded in meeting our claims. الشغل اللي بعرض لكم هو كان collaboration مع معالي الدكتور هاشم يماني. الحقيقة we were working on something totally different. Most of you اللي أنا تعالى فكرة بين العربي والإنجليزي. If there is a problem في أحد ما عربي عنده مشكلة okay then I can switch back and forth. But if it's a problem hey okay ممتاز أحسنت. I will be switching between Arabic and English. If there is a problem, you guys have a problem with Arabic, then I could just totally do it in English. So is that okay? Can I switch this? All right. Okay. But if there's a problem, I can always meet you guys after the lecture and then... Okay. So this was a collaboration with Dr. Yamani. In research, usually you have a line and you want to pursue your problem. But sometimes, or most of the times, you find a divergence. You meet a problem. يعني, there is a difficulty. So you divert a little bit and you try to solve and come back. Sometimes the divergence is so interesting, so beautiful. Just continue. You forget about your original problem. I think some of you, from the way I see your faces, you have met this more than once. So this is one of the problems that we were facing. We were working on some physics problem where orthogonal polynomials are essential, and we had this problem, so we diverted and we found out this very interesting results. I hope you will agree later. I have to demonstrate to you what is the interesting stuff in this work. Okay, I guess most of you know what polynomials are, I assume, since you are mathematicians, physicists, and engineers. But if you don't, then what you need for this lecture is very simple. For those of you who don't know what are the orthogonal polynomials or polynomials in general, I think all of you know the quadratic equation. If you have three numbers A, B, and C, then you can form the object, which is ax squared plus bx plus c. If you say it's equal to 0, then you're solving for the values that make this object equal to 0. This object is called the polynomial of second degree. Okay? That's basically, and if you have four numbers A, B, C, and D, then you can form ax cubed plus bx squared plus cx plus d equals 0, and that's called a polynomial of the third degree. Okay? So that's what you need background for this. Okay. By the way, I'm sure we use in science and engineering polynomials left and right. But believe me, if you go just Google it in the internet, say application of polynomials, ooh, it's amazing. You will find in finance, in traffic, in the weather, in medicine. It's amazing, everywhere, in the arts. So the application of polynomials is all over the place. It's very nice objects, okay? And there is a big line of research and a big area in mathematics called special functions and polynomials. Some of our friends that I collaborate with work specialize in this area. Okay. There are certain properties of these objects, polynomials. One of the most important properties of these polynomials is what they call their roots or their zeros, which means that the value of their argument that make the object, the polynomial, equal to 0. Now, it has been well established since the 1800s. I think there was a Norwegian mathematician, Abel, who proved that polynomials, okay, well, you know, a second degree equation has an exact solution, right? A third degree equation or polynomial has also exact. The fourth order also has exact, but probably it's not well known, very common. Now, this guy proved, and it is rigorous proof, that you cannot have an exact roots for polynomials of order greater than 4, 5, 6, 7, 8. There's no exact formula. Well, we have given that, and people want these zeros, so just do it numerically. So there was a race of people trying to find the roots of polynomials of degree greater than 4. And everybody once in a while comes up and say, I found a better way to do it, more efficient in accuracy, in convergence and all of that. Claim, I hope to show you by examples. We found a simple method, but we found out, and to the best of our effort and all the people that we know around the world, that we know, it is the most accurate method so far. We tried all the software programs that people use, MathCAD, Mathematica, MATLAB, Fortran, packages here and there, it's more accurate. And in sometimes it is faster. Okay? In fact, I don't want to claim more than what I cannot stick my neck out. But all the programs that our friends tried all over the world, it's faster. Okay. So big claims I have to. That's why we had a problem here trying, because I have a demonstration for you. I want to demonstrate this. And yeah, so I hope to convince you of that. Okay, there's something I need to explain here. Fibonacci, what is, I think maybe, anybody here from Algeria, from Al Jazair? Anybody here from Al Jazair? Okay, nobody from Al Jazair. Anyway, I was hoping that somebody is here. So, yeah? Algeria? Okay, maybe you know this story. Fibonacci is a very famous mathematician in the 12th century. He was born in Pisa, Italy. And his father was a merchant. He was a trader يعني. بين إيطاليا وشمال أفريقيا. فهو كان وهو صغير يروح مع أبوه. يروح يجي مع أبوه. He spent a lot of time في بوجايا في الجزائر. It's a city on the shore, on the Mediterranean in Algeria. And in the 12th century, it was very active in science. And so Fibonacci, he spent a lot of time مع أبوه يعني في الباخرة. فجلس في بوجايا بالجزائر فترة يعني سنوات. إيش أتعلم هناك؟ أتعلم الأرقام العربية, the Arabic numbers. At that time, in Europe, it was not known. People do calculation with the Roman numerals اللي هم واحد كده, 2, 3, 4, and if you try to do computation with those, good luck. Okay. So he was really يعني amazed by the Arabic numbers. Arabic numbers اللي هي, we know the decimal numbers, 0, 1 up to 9. So he actually made a book. He authored a book which was very popular in Europe for many centuries. It's called the Book of Computation. Okay. By the way, his name is not Fibonacci. بس إيش معنى Fibonacci? Fibonacci means the son of Bonacci. يعني ابن Bonacci. So you start wondering why Fibonacci? Now I tell you why. This is now the 12th century. At that time, if you are a big and good scholar, كنت تسمى ابن رشد, ابن البيطار, ابن الهيثم, ابن سينا, ابن النفيس. So that's the origin. So he has to be called Ibn something. يعني at that time, that was the influence of the Muslim and Arabic science on the world. So hopefully one day, inshallah, we'll go back to that and we have a better contribution. Well, I don't know his name actually. Very few people. You can, of course, Google it and you can find his exact name. But everybody knows Fibonacci, and there is a periodical now under his name. Nardo, well, it could be. I don't know. للأسف. يعني very few people actually. Puccini, huh? His name? Okay. All right. So let me. It's a long introduction. I'm sorry. So let me start with. This is our starting point. Let me start. What is Fibonacci numbers? They are a sequence of numbers. How do you find them out? Each number is the sum of the two previous ones. Okay? So what you need to do is you have two initial numbers, and then you build the rest using those. Usually, the first initial ones are 0 and 1. Usually, not all the time. So they are like this. 0, 1, this is the starting. So the second one is the sum of these two, 1. And this one is the sum of these, and so on, all the way. Okay? So these are Fibonacci numbers. Now what is special about these numbers? Let's take the ratio of, let's take the ratio of each number to the one previous to it. Okay? 1 over 1 is 1. Of course, you cannot start with this 1 over 0. 1 over 1, 1. 2 over 1, 2. 3 over 2, 1.5. 5 over 3, and so on, and so on, and so on. You see, after a while, the ratio becomes closer and closer to a certain number. Okay? And those of you who are obsessed with the numbers, you know what this is. This is called the golden ratio. Okay? The golden ratio. Now, let me prove to you that this is a golden ratio. That's our starting point. So, now we know this relation. Okay, this is how you calculate the Fibonacci numbers. So let me divide this equation by this thing. If you divide it, you get this. Fn plus 2 over Fn plus 1. And this one, Fn ala Fn plus 1. But I invert it. So you get this. So after, if n is large, after this number is the same as this number, right? After we have seen it. So if I call this after long, when n becomes large, or if too much. So I get this z equals 1 over z plus 1. Multiply by z each side, you get this, and this equation you can solve and write with the plus sign. This is the golden ratio, right? I mean, if people know what the golden ratio is, then this is 1 plus square root of 5 over 2. Okay? So, let me demonstrate this for you. Let me show you that you can get this ratio for. All right. So, remember I said you start with 0 or 1. Actually, you can start with any two numbers. It doesn't matter. So here I started with, if 0 is 2i, is even complex. And if 1 minus 7. Okay? And this is the way I calculate the rest of the number. And this is the ratio. Okay? And I continue for 20 iterations. 20 numbers. Okay? So let's see if we get, the golden ratio is this one. So let's see what do we get after 20. So these are the numbers. I started with 2i, and the second one minus 7, and this one is the previous sum of the previous two, you can see, and this one is sum of the previous two, and so on and so on. And this is the ratio. You can see that it is getting to closer and closer to a fixed number. And this is the golden number. Let me find the difference. You see, this is R, the ratio, for large, when n becomes 20, so I get this capital Rn, and I find, and this is it, this is the value. The difference between this Rn and the golden ratio is this one. Let me see. The difference is, you can see 10 to minus 9 difference. Of course, if I increase n larger, let me make it, let's say 50, for example. And I'll run the program. Oh, too much. So, it is exact now. The difference is 0. Okay? After 50 iteration. Okay, so far, nice, but still nothing new. Okay, so at least I demonstrated that the ratio of two consecutive Fibonacci numbers is the golden ratio. In fact, there is another thing. What I have done is actually solve this equation. Right? I have actually just solved this equation, right? Okay. So let's say, since I am calling this constant number, so let me call this one Rn plus 1, then this will be Rn. So instead of starting with two numbers, F0 and F1, I will just start with one single number. I call it R0 and iterate. So R1 will be 1 over R0 plus 1. R2 will be 1 over R1, which I already found, plus, and so on. So if that is the case, so I don't need for the iteration two numbers, I just need a single number. Okay? So let me show you at least the same, but so here you can see this is the equation I gave you, and I started with initial number. I can choose actually any number. Let me change it even now to something different, 27, for example. So any number, any two numbers. Now let me run. This is the golden ratio. So if I run this 50 times, I get this ratio is the same as the golden number, except a difference 10 to minus 24. If I make it even larger, it will be almost identical. Make it 500, let's say. Oh, it's the difference is minus, يعني after the decimal point, 212 zeros. Okay, so this is a very good way of doing it. يعني using two numbers, just one single number. All right. Again, nothing new here. So I'm just solving this equation. Now, how about I don't use this equation, general second order equation, which with B and C. By the way, I take A to be equals to 1. You can always that, or divide the whole equation by A. So this is called monic polynomial. It means that the highest degree has a factor, coefficient 1. Okay, but you can always do it by dividing by that non-zero. Okay, so let me, instead of this equation, I write this equation. Well, if I do, then I get, if I divide this equation by Z, I get this equation, which looks like this. Remember the original equation, Z is equal to 1 over Z plus 1. So instead of 1, I put minus C. Instead of 1 here, I put minus B. So hopefully, if I do that, repeat the same thing, but choose, instead of 1, 1, I choose minus C and minus B. I solve this equation. Okay? Well, let's do it. Okay? Demonstrate that, yeah, I get a solution, which should be one of these two solutions, right? Simple. Now, I'm just trying to show you that what I'm going to do next is trustworthy. So here I'm just trying to see the things that we know, we normally know. Okay. So here, I chose these simple, B and C like this, simple, so because I know the roots of this. One of them is 1 and the other is minus 3. So very simple to see. And this is the equation. Remember, it was 1 and 1. Now it's minus C and minus B. And I took the same initial, you can choose anything in fact. So hopefully I get one of the roots. So let's run it. The roots are 1 and minus 3. This one, after the iteration, I get the minus 3. Minus 3 plus 0, after 49 zeros after. So this proves to be only for 100. It's accurate evaluation of one of the roots. Okay? Right? So, يعني, still I'm just solving a second order equation here. Yeah, we found one of the roots. So how about, what about the second root? Right? We found one root. How do you get the second root? Well, very simple. If you have one of the roots, I can write the polynomial, which is this. If I have two roots, I can write them this way, right? Factorizing. Then this equation can be written this way. Okay? Therefore, if I know R, one of the roots, then W is calculated this way. If I know this R exactly, then this will give you W exactly. But if I don't know R exactly, approximately, which is a good approximation. So what I'll do it iteratively. So this equation, I will call this Z some W, this Z is Z, and this one is the improved one, the iteration. So let me show you that if I do this, I get actually the second root. Okay? Here's my mouse. Okay. So remember this Remember this is finding the first root. Huh? I have an initial, I call it little r, so that I distinguish between the new and the old. So this is finding the first root. We know it before. And I will call this r the last one here. And then I enter it in this equation to get the second root. So let me run the program and hopefully get the second root. So the first root, I know it, I got it, -3. Now, I actually intentionally made the accuracy very low for the first root. This is the first root, -2.99. There is 10 to -6. But look at the second root. Second root, we know it's 1, huh? 1 and -3, the exact value. The second one is 1. Amazing, this equation, huh? This is the heart of our program, this equation. Dating the polynomial, huh? Okay, so this is the magic equation, and you can see how we second root. If you, of course, increase the iteration, you get it 10 to -500 or something. So don't go that far. Okay. Right. Now, I've been talking about second order differential, second order polynomial, second degree polynomial. Equation, huh? Pairs. Everybody knows how to solve that. Okay, now I want to go general. I want to see, now because I really had good trust, at least in the first. So, let's say now I go to any general n, and these are complex coefficients, complex, huh? So what I do, I factorize. I don't know the roots, but I factorize assuming these roots. And let's say I take this one, I divide both sides by all of this quantity except this one, which is that. Then I say z equals z0 equals z minus all of that. And now I do this iteratively, because now you have seen the iteration was very nice. So let's say, so if I know all the roots except one, I know all the roots except one. This is the way how I do it, to find the missing root. So I'll start with the known roots, and I want to find the missing root. So the known roots is this, they are here, and the missing root is z0, which I do it iteratively. You see, just like the previous slide, but now it's for a general order, degree. Let me show you that yes, I get the missing root very well. Okay. Now, of course, all software programs, Mathematica, MATLAB, they can't find the roots of polynomials, right? Now, I'll show you that we do better, the accuracy. So what I do, I ask my program to calculate the roots, and I will hide one of them, اللي هو z0, and I tell my program find that z0. Okay. Now, how do I know that my root is better value than the root found by the program? What I do, I just substitute the root I found in the polynomial. If it gets me exactly 0, wow, I succeeded. Usually, of course, 10 to -15, 10 to -13, 10 to -7, yeah? So I do the same thing for the program itself, not my routine, and I see which one is smaller. The smaller is the more accurate, right? Ideally, it should give you 0, identically 0. But because we know it's computation, approximation, all of that. So let's see. Let me show you. I will get a better one. This is, by the way, MathCAD code, and it's a powerful program, just like Mathematica. Okay. Okay. Now here, the start of our magic, let's say. Okay. Okay, fine. Let me go. Okay, here I'm looking at polynomial of degree 20. And these are the coefficients. So the first coefficient, A0, remember this is the polynomial. Let me just show you. remind you of the polynomial. How does it look? This is the polynomial. Zn, an minus 1, zn minus 1, and so on, up to a0. So these are the a's. Okay, I'm just choosing randomly, by the way. Yeah, I just like that. You can choose anything. So the first one is 2 plus 3i, minus 1, minus 7, minus 3, minus 7i, 5, and so on. So these are the coefficients of the polynomial. There is a routine in my software here called MathCAD called polyroots. You put the coefficient, it will give you all the roots. And these are the roots here. Where are they? Yeah, here. See, these are, I just plot them in the complex plane. Okay? These are the 20 roots of the polynomial. And Z0 is this one, the one with the circle. You see that? Do you see it? This one. Okay. Now, this is what the program gave me for Z0, minus 1.19, blah, 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 and 0.3i. Huh? This is the routine I'm using. If you remember the formula, it's this formula, right? This is the formula. Okay? This is exactly, this is it. Huh? This is just a product of, okay? I use this, and I use all the zeros except Z0. As you can see here, I'm summing from m equals 1 to n minus 1. So I'm using roots 1, 2, 3, 4, up to 19. Okay? Z0 is not there. So I calculate Z0, and the computer gives me Z0 from the software itself. So the difference between them, this is what the computer gave me, and this is my calculation. There is a difference of 10 to minus 11 in the real part, and 10 to minus 10 in the imaginary part. So I ask, which one is more accurate? So I substitute the polynomial in Z0, I get 10 to minus 7. Okay? Not exactly 0. Okay? 10 to minus 7, which is reasonable. Now, what about my program? And remember, every time, it's iteration. The first iteration is very bad because I'm giving, you see, this is my initial, I'm proposing initial root, which is, of course, different than this one, 24 minus 7i. This is completely way from the root. Huh? You can actually put any initial value. Huh? So the value of the polynomial, and then I find the successive roots. Huh? And here what I get when I substitute what I found in the polynomial. The first one, 10 to minus 4, lousy, far away, it's not good. That's my initial guess. But look, immediately after that, 10 to minus 11. The second one, 10 to minus 13. 10 to minus 13, and probably it stables at 1 times 10 to minus 13. But compare this to 10 to minus 7. Almost several order of magnitude. Twice, 10 to power what? 10 to power, twice its accuracy. 10 to 6 order of magnitude. It's amazing. We call it amazing here. I'll try later to explain how this came about. It's mysterious. It was mysterious for us for the time, for a while, until we understood it. Now, okay, so here I just demonstrated to you that if I know all the roots except one, I have a very good way of calculating the missing one very accurately. Now the exact, and here's the challenge. If I don't know any of the roots, okay? Now here where the muscles come in. So, what if I don't know any of the roots? I don't want to take it too long. So he usually here I start with the second order equation, blah, blah, blah. So let me skip that and go to the meat, just to save time. Okay, now for a general case. I don't know any of these roots. I don't know any of them. Here's what I do. Let's say this is a polynomial of degree n, and it has n roots. So what do? Give me any n initial guesses. Random. Choose them randomly. Any initial guesses. Okay? I will call them tilde, z0 tilde, z1 tilde, up to zn minus 1 tilde. These are in numbers. These are my initial guess, and they are random. The way we do it in our program, actually, what we do, we draw a unit circle in the complex plane, and we choose all the endpoints on the circle. Okay? That's for any polynomial. This is actually عشوائيا, right? This is just a... No, it's very simple. Maybe I think the accuracy can improve if you are smart enough to choose a good guess. But we came stupid, say, for all our polynomials, any polynomial, I'll just use a unit circle, put the numbers in them. Yeah. That's. However, I tell you, in secret, we did different way, like spirals and the different distributions, and we found better. But I'm just giving you the easiest, simplest way. So then I do the iteration. Now what I will do, I will first start to improve on this one. Yeah? I will try to improve on this one, using the rest of them, which are arbitrary, random. Okay? I use this. So I'll iterate many times until, let's say, from m equals 0 up to n. So the final one is Rn plus 1. I start again with this arbitrary one that I chosen. And then after the iteration, I get something, it's different than Z0 tilde. I'll just call it Z0 bar, okay? Which is the last one, Rn plus 1, okay? Now, I hope this is a better estimate than Z0 tilde, okay? Now, the next thing, what I do, I will try to improve on this dumb guess or initial random guess. So what I do, I use the rest of them except that Z0. I will not use the old one. I will use the new one that I found by iteration, the Z0 bar. Okay? You can see then here Z0 bar, while the rest are Z2 tilde, Z3 tilde, the old. Yeah. Hopefully this is an improvement on Z1 tilde. So I call this Z1 bar, okay? And I continue with this process. So for example, I will improve on Z2 tilde by using Z0 bar, Z1 bar that I found already, okay? And the rest that are arbitrary. So I get Z0 bar, Z1 bar, and Z3 tilde, Z4 tilde, Z5, and so up to the end. And I call the last one Z0 bar, and so on, until I get all of them. Okay? So now the question, how correct are those? Again, what I do, I substitute in the polynomial. If it is 0, wallahi, يعني luck. I was lucky. Usually, of course, it's not. So you see it's 10 to minus 15 or 10 to minus 3. So, well, I don't like it. I want to improve on this. So you repeat the same procedure. But remember, the first procedure we started with Z tildes, Z0 tilde, Z1 tilde. Now I will repeat the same procedure, but I start with the bars. Z0 bar, Z1 bar, the new ones that I found. And then I get a new set of roots. Let me call them Z0 double bar, Z1 double bar, Z2 double bar. And I substitute in the polynomial. If the accuracy is much improved and my satisfaction, I stop. If I need more accuracy, I repeat the same thing. Okay? So, let me demonstrate that this is really fantastic and it's working. And I will use the same coefficients before, but later I will... Come on, my mouse. Here. Okay. All right. So my numbers in, where are they? Yeah, here. I think I plot them, huh? The 20 numbers, I plot them somewhere. Are they somewhere? Well, anyway, they are the same numbers. Here they are. These are the A's, the previous A's that I showed you before. So I'm doing the calculation for the same polynomial. Okay. And this is the program, we call it Khandaq. The reason we call that because Dr. Hashim and I, made this work together في المدينة المنورة في مدرسة ثانوية in a high school called خندق. So in dedication to them, and we call the software, the program, we call it خندق. مدارس الخندق الأهلية بالمدينة المنورة. Okay, the program is here. Let me just give you, it's in blue. So this is the polynomial, if you just write it in programming language. And this is the initial guess. You remember I told you it's in the unit circle distributed over a unit circle. This is a unit circle. Z is amplitude 1 and phase 2 pi m over n. M is 0, 1, 2, up to n minus 1. So it is distributed actually evenly on the unit circle. And this is the final. Remember, this is the program. This is the formula, the essential formula, Rm plus 1 Rm and all of that. So it's here. R equals R times F, which is the polynomial evaluated at those points, over pi, which is the product. This is this product, yeah, which is here in one of these. Okay, so that's the program that I told you. And then I found the roots, and I repeated this calculation 5 times. Remember I said, if you're not satisfied for the first time, repeat the same process, but start with the good roots that you found. So I repeated 5 times, and I used an iteration of 10. 10, and repeat, 10. And then I found the roots. 10, find the roots. 10, find the roots. And that's 5 times. Here is what I got for this polynomial. Remember, the computer gave me, well, I didn't use the full power of MathCAD. It gave me 10 to minus 7. Here, these are the roots that I found with the program Khandaq, and these are the accuracies. Okay. By the way, this 000 actually is a number less than 10 to minus 307. MathCAD does not recognize any number less than this. So one of the roots is 10 to minus, less than 10 to minus, when I substitute in the polynomial. The rest are 10 to minus 16, 15, 14. Yani, this is, I use single accuracy. If you do double accuracy, you get 10 to minus 32, 10 to minus, and so on. Yeah? Let me, actually, this is very interesting, this one, which is very accurate. Which one? Which is this root? You see, these are the roots that I found. You see, this guy, one of them, these are 19, and the 20th is here. This guy is very nasty. This is the one that all other programs in the world give you the worst accuracy for this one. The one which is far away from the jama'atu. Yeah? This guy is the least accurate in all programs that we have seen. It is the most accurate in our case. It's we did not believe it for the first time, but anyway, that's what we got. In fact, we try and we looked not just the accuracy of this one, the rest of them. Still, it's more, our calculation is more accurate. I will demonstrate now that for all of them, and I will actually generate these polynomials randomly. So you don't see you fix them, it's just random. I just choose the A's randomly and I find the roots. Okay. I'm getting close to finishing, so thank you for bearing with me. Okay, so okay, في MathCAD في شيء يسموه polyroots, and it has two methods, the Laguerre, which is less accurate, and the companion matrix method, which I use in the comparison. Our routine? These. I think they use, so this one is the Laguerre method, and this one, they call it the companion matrix method. I think it relies on tridiagonalization and Jacobi matrices and all of that, yeah? Yeah? So, but we also compare it to Mathematica. There is a program, I think those of you who are they work with Mathematica, there is these programs called Reduce, InRoots, InSolve, yeah? Okay? These also find the roots of polynomials or functions. And in Fortran, there is a library called Static Common Mathematical Library. People who work with Fortran, they're familiar with these. These things find the zeros of polynomial, okay? And also we compared with Mabel, MATLAB, etc. And every time, our routine is more accurate and faster. I can only claim that it is more accurate now, but I cannot claim that it is absolutely faster. Okay? But all what we have seen, all the tests that we have done, hundreds of tests, different programs, it is faster. Okay, now let me demonstrate to you. Since I only know how to program in MathCAD, I will show you the roots that is found by MathCAD and the roots that I find with my software, my program, my procedure here, and I compare the accuracy. Remember, the accuracy, you just substitute the roots in the polynomial. If you get 0, that's khalas, you are very successful. You get analytic answer, but you don't get 0. How close to the 0? If you are closer to the 0, you are better, right? Okay, so let me demonstrate this to you. Okay, now I'm using 50, a polynomial of degree 50. Yani you have 50 roots, and it's complex, in the complex plane. Yani you cannot get worse than that. These are the coefficients. The distribution you see here are the coefficients of the polynomial in the complex plane. And these are the roots of the polynomial, okay, that I found. Of course, the computer, remember I said there is a statement in MathCAD called polyroot. It will find the roots of a polynomial. In fact, it can find the roots of polynomial up to degree 200. After 200, MathCAD, you go like, oh, sorry, I cannot, this is too much. And I can go all the way to 500, and we did that. Or more even. For 500, I think it took about 3 point some seconds or something. I think 500. I don't remember exactly, but I can send you exact information later. Okay, so here I took 50, and this is a random generated orthogonal, coefficients of the polynomial, and these are the roots, the 50 roots. You can see 2 of them are stubborn, they are far away. These are usually the least accurate field programs. Okay, now let me compare my accuracy to the program accuracy. To the left is the accuracy, which is, again, the accuracy is substitute the ones you found in the polynomial. This is my result, this is the computer result. So you get this one, 0 for me, yani 10 to minus 3 or 7 or less. And this is 10 to minus 18. 10 to minus 19, 16, 18, 16, 16, 15. You can see consistently that my accuracy is better. Now, let me just change the polynomial. Remember? Here I can do it by one click. The mouse is stubborn here. These are the coefficients, right? So let me change them. I just click on this one. This is nice about, I like this MathCAD program. Just run again. Oops, it changed that. So the coefficient has changed, and the zeros, of course, have changed. Only one stubborn here, this one. And the accuracy, it is closer now, but still I am more accurate. This is 4 times 10 to minus, I am 3 times 10 to minus 16. 15, 16, 15, 16, 15, 16, and so on. Yeah? Change again, run again. Okay, so these are the new coefficients, and these are the new roots in the complex plane. And the accuracy, 15, 17, 15, 16, 14, 16. Yeah? So you see that my accuracy, the value of the polynomial at the roots is closer to 0 than the MathCAD. The same thing for Mathematica. We use all these in roots, in solve, reduce. We did that. I didn't do it. My friends did it because my students, I don't know. Okay. I can actually stop here. So this is a procedure. Okay, you ask, where does this accuracy come from? Well, I'll tell you. First, when we met it, it was like black magic for us. We didn't know what's happening. But the essence of this are two factors. One, the iterative routine, the convergent iterative routine, which has a lot of features of what we call the continued fractions. If people are you familiar with powerful calculation, or continued fractions is the best way to do the calculation, because all the time you are dividing by something big, dividing, so numbers get closer and closer and closer. Convergence is much better. That's one. That's not the whole story. There are several, like Newton-Raphson method or something, still they have do this. But here there's an extra thing. Let me show you. Mathematicians say this is simple. I mean, it's obvious. But for people with the calculation, it's not so obvious. Let me show you the magic formula. Very simple, very simple. How do I go back? Use this. This is the magic. This is the magic formula. This one. This one. Remember, here we're talking about second order equation. Huh? I mean, polynomial of degree 2. If I know R exactly, one of the roots, okay? Remember, this is the basis of our formula. This is just extended for more than 2. What this equation tells you, it tells you that if you know R exactly, then I can find W by substituting any value of Z. Put any value of Z. You get exactly the other root. Any value of Z. Of course, don't choose Z equals R. But يعني it's one point in the complex plane. But choose any other infinite points. If I know this exactly, I can find out this exactly. Choose any R, 0.5, 2.3i, anything. Okay? This will give me, of course, mathematically, this is obvious. But computationally, this is strange. The right-hand side depends on Z, variable. I put to the right side any number I choose. Except, of course, I said Z equals R. Choose any number. It will give you the exact answer to the left. This is amazing. يعني, let's not talk about two mathematicians. Huh? How isn't amazing? It's amazing. يعني, you get an equation to the right. It's a function of arbitrary number. To the left, it's always the same. Of course. يعني, understand this, cooperate with this, and to give you that number. Okay. So this is actually the magic formula. Beside the continued fraction concept, add to it this. You got it. That's a magic formula. هذه recipe, magic recipe. I have a challenge for you. Prove me wrong. Do any, if you ask me, choose any coefficients of the polynomial. You find the roots and give me those coefficients. I find the roots. Mine will be better than yours, more accurate than yours. Of course, don't use my method. Use whatever method you like, but not mine. Yeah? I'm sorry, I always say mine. It's Dr. Hashim Yamani's and mine. We are actually trying to, in the process of getting patent for this method. We'll see how it goes. So, we open the door for questions? Yeah, okay. Thank you. Well, I really am grateful to you for coming. Yani, I know the hardship, and you just had probably to fight with your wife to come, and yeah, it's closed. What do you want to do there? Oh, inshallah. Yeah. Yes.
when you use the simplex method, you are not in the worst scenario. You always, when you plug in your initial data and work on it, it happens that you are not in the worst scenario. So people are fond of the simplex method rather than the ellipsoid method because of practically when people analyze, they take the worst scenario for this. So have you done analysis in the worst scenario, comparing your method to the others?
We didn't. We are asking a lot of people who are, in fact, this is more of a programming issue than a hardcore analysis. We are the first step to ask people who do programming to find the efficiency, which means accuracy, convergence, speed, and stability. These 4 issues, we have to have experts who in programming or to reserve this. Remember that here we're doing ad hoc. We're physicists, and Dr. Hashim, we don't know how to, but we found this flower and we just try to smell it. So what we do, remember I said, repeat the procedure again. How many times I repeat? If I do eventually a program, I should relax and let it do everything. But here we intervene. Well, it's not accurate for 10. Let me do it 20, 15. Let's do and there are optimum values of the number of iteration. If you increase the iteration more, you get worse results. So there are issues like that. But if I intervene and take the best case scenario and compare it to the big muscles, like people who have packages in Fortran and who really know how to do, we succeed. So it is, you're right, we have to have a second step now. People who can look at the efficiency of this routine and try to improve in it without my own intervention as a programmer. I won't sit there, relax, give him all the coefficients of the problem and tell him, okay, find me the most accurate ones. We cannot do this yet now. I can only intervene, do this, do that, and I give you something, and I say, I challenge you to do whatever way you like. So yeah, there is a lot to do in this area, and not just from programming, but as you said, the error analysis and all of that, to really find out what are the best application for our procedure. I'm sure there are other methods. If I want to make it automatic, there are other methods that outperform it. Yeah. A good question. Thank you. Any other? Yeah.
About what is the difference between your method and Newton method?
They are all iterative. The Newton method is iterative, and one thing we analyze that actually there's Newton method has bifurcation features. They make what do you call it? They give you a diagram. When you make certain initial guesses, then you have to know which area in the region of you might get. For example, if you start with the Newton method that has different solutions, you start with a guess. You might get one or the other depending on where you are in the complex plane with your initial guess. And if you do all of those, you'll get some diagram. I don't know what they call it. They call it. Yes, but if you look at the all possibility, there is a diagram that it produces. Very nice diagrams. Yeah. So those are our method does not have this feature of let's say, because it gives you all the roots at once, and wherever you start, it doesn't matter because I remember I said start random. So let's say the Newton method has some structure built in it different than this khandaq routing.
Okay, first of all, I would like to thank you, Dr. Abdulaziz, for your nice presentation. I have two questions. First of all, did you study the order of convergence of this method? And secondly, if I can take a look at the formula, can I take a look at it, please? The general. Okay, thank you. This one. Now I don't know what will happen now if the roots are very close to each other. I think it will blow up, right? It will blow. Huh? Exactly. Yes. Yes. Does this solve the problem if the roots are very close to each other? Because the numerator will be very close to zero. So. Yes. And the order of convergence of this method.
Yeah, now you ask that tough question. We are not expert in this. We are asking people, some expert. Actually, we are in communication with one guy in San Diego who is very good in, and he's working on it to give us a sense of the four issues: convergence, accuracy, and speed. That's يعني it needs a حياك الله. يا هلا ومرحبا.
Is there a way to tell using the when you have exact roots, and can you recognize them?
I cannot beat Abel, the Norwegian guy who found the roots exact. I'm not a mathematician, يعني. I really cannot answer this question. I don't know. If you know the exact roots, I can tell you how far I can come close, but I cannot really, I don't know. In fact, we had even a better question, which is important to, raised by your actually intention. Which is very important to encryption and coding. We wanted, if we can succeed in finding the polynomials that whose zeros are the prime numbers. If we could, we're actually working, trying to do that, see if we can actually make our method generate polynomials with roots that are only prime numbers. If we can succeed, then we'll not get just fame, but money. But I think we will not be able to do it. Number 5, huh? No. Mm-hmm. Uh-huh. Well. Really? Yeah. Oh, والله I get بعدين then I want to see all the time we're searching for people having better way of doing it than us, then we can stop claiming that we succeeded in fact to find polynomials that generate prime numbers, but only very few order. We want to, if we can go up to few thousand, then we're in business. And if we can find the first few thousand prime numbers by a simple method like this, then so you can use those polynomials, substitute anything, and you get the prime numbers, and you can use them in coding or deciphering.
Provable not to have any polynomial that produces prime numbers. This is proved, of course. I mean, yeah, but I mean, you are aiming at the, at the bigger primes. So, yeah. Yes, yes. And these are important in cryptography. So, yes, yeah, thank you. Yes, yes, yeah, yes.
Yeah.
اولا جزاك الله خير دكتور على هالمحاضره الجميله. حقيقه انا ودي اكد I just would like to affirm what Abu Ahmed said. It's theoretical analysis actually it's the value of the idea. I think I'm happy that you contacted the San Diego guy to contribute in this side. He can, I think, analyze what you want here. And can you just a little bit go back to the previous slide? Yeah, I think this one. Yeah, I think this is